It's 3 in the morning. The test passed on your machine, failed in the pipeline, and passed again on the rerun. 6 hours later, you find it. One character, one wrong assumption about what a value actually contained. Debugging feels like talent. It isn't. It's a search procedure and it can be taught. Here's the frame that changes everything. Debugging is a search. You start with a space of possible causes and every action should shrink it. Bad debugging is changing things and hoping. Good debugging halves the space of possibilities until only the truth is left. Because a bug is not broken code. Your machine executed your instructions perfectly. A bug is the gap between the program you think you wrote and the one that runs. So every technique here does one job. Close that gap with real observations from a running system. 9 steps. Step 1. Make it deterministic. If you can't trigger the bug on demand, you aren't debugging. You're sampling a random process and guessing at its shape. Flaky is not a property of a test. Flaky means there is an input you haven't identified yet. And that input is almost always one of 5 things. The clock, the seed, thread scheduling, test order, or state left behind by whatever ran before. So pin them, freeze the clock, fix the seed, force single-threaded execution, shuffle test order until it fails, then lock that order in. Now it feels the same way every time. That isn't preparation for debugging. That is most of the debugging, and make it fast. A 1-second reproduction lets you test 60 hypotheses a minute. A 5-minute one gets you 12 an hour. Shortening your feedback loop is the highest leverage move of the session, and it always feels like avoiding the real work. Step 2. Shrink it. Take the failing case and start deleting. Remove a dependency, drop a config flag, have the input. After every cut, check it still fails. This has a formal name, Delta Debugging, and you can automate it. Have the input, still fails, keep that half. Passes, take the other. Either you delete the cause and find the bug by accident, or you're left with 20 lines that fail instead of 20,000. A minimal reproduction also turns an unanswerable question into a bug report someone else can fix in 4 minutes. Step 3. Read the evidence properly. A stack trace is not an error message. It's a snapshot of the call stack the instant things broke. Each frame is a function waiting on the one above it. Read from the top down and find the first frame you own. Everything above it is usually library code doing exactly what it was told. If your language chains exceptions, the message on screen is the last symptom, not the first cause. Walk the cause by chain to the bottom, and be suspicious of asynchronous traces. When work is queued and resumed later, the trace shows the machinery that resumed it, not the code that scheduled it. And read the actual values in the assertion, not just that it failed. Expected and received are 2 facts. The difference is the clue. Step 4. Instrument before you theorize. Staring at code and thinking hard feels productive, but your mental model is what's wrong. You can't repair a broken model with the same broken model, so get observations out. Printing values is crude, unfashionable, and every engineer you respect does it daily, but do it properly. A bare value scrolling past is noise. Print the name, the value, and where you are. Better still, log structured fields instead of sentences. Then you can filter and query your logs instead of reading them, and log at boundaries. What went in, what came out. Most bugs live at the seams between components, not in the middle. In anything distributed, attach one identifier to a request and carry it through every service. Without it, you're reading 5 unrelated stories. With it, 1, and print the type, not just the value. Text that looks like a number prints identically and behaves completely differently. Step 5. Learn your debugger properly. Most self-taught engineers never move past printing. That's the biggest capability gap I see because a debugger doesn't sample your program, it suspends it. Here's what actually happens. The debugger swaps the instruction at that address for a trap. The processor hits it, raises an interrupt, and control passes to the debugger. Your process stops where it stands. In interpreted languages, it's the same idea one level up. Before each line, the runtime checks whether anyone asked to stop here. You're now standing inside a frozen program, with every value in scope in front of you, not what you assume they are. What the are. First, conditional breakpoints. Don't press continue 400 times waiting for the bad iteration. Attach a condition and stop only when the identifier matches. Same idea with a hit count. Break on the 1000th call, not the first. Second, log points. Breakpoints that print and keep going. You get print debugging with no editing, no rebuild, and no redeploy. Third, the one people miss. Once stopped, walk up the call stack. Select the frame above you and inspect its variables, because the wrong value here was usually built 2 frames up. Debugging the frame that crashed is debugging the victim, not the culprit. Fourth, know what stepping does. Step over runs a call and stops after it. Step into descends inside. Step out finishes this function and stops in its caller. The strategy is simple. Step over until something looks wrong, then rerun and step into the call that broke it. Fifth, watch expressions. Instead of hunting for a value every time you stop, pin the expression you care about and watch it change as you step. And if your tooling has it, the data breakpoint. Don't ask where this value gets corrupted. Tell the debugger to stop the instant that memory changes. You can also attach a debugger to a process already running, inside a container or on another machine. Nothing has to restart. And when a process has already died, post-mortem debugging loads its core dump so you can inspect the corpse. Full stack, full state at the moment of death. 10 minutes with your debugger's documentation will return more than any framework you learned this year. Step 6, bisect everything. You know the idea. Don't read 1,000 lines. Probe the value at the halfway point. Healthy means the fault is downstream. Wrong means upstream. 1,000 lines becomes 10 checks. That isn't a trick. That's just what having does. Now apply it to time. If this used to work, the cause is a single commit, and your version control system will find it for you. Mark 1, commit good, 1 bad. Bisect checks out the midpoint. You answer good or bad, it halves again. 10 steps through 1,000 commits. And automate the answering. Hand it a script that exits 0 when things work, and it finds the guilty commit with no further input. Then bisect the environment. Works on my machine but fails in the pipeline is not a mystery. It's a diff. Compare runtime versions, environment variables, locale, time zone, memory. Bisect the data too. If one row in 10,000 breaks the job, halve the file. The failing half holds your answer, and bisect the stack itself. Your code or the library, your service or the one it calls, client or server. Each is one probe in the middle. Step 7. Work like a scientist, not a mechanic. Before you change anything, write the hypothesis down. This value is empty because the cache is read before the write completes. Then write the prediction. If that's true, this log line shows an empty result and the 2 timestamps overlap. Then run one experiment that can prove you wrong, not one that makes you feel right. Confirmation bias is why smart engineers defend for a day a theory that evidence killed in 10 minutes. Change 1 variable at a time. Change 5 and it works, and you fix nothing. You have a working system and no idea why. A bug in witness protection. Keep a lab notebook. 2 columns. What I tried, what happened. 40 minutes in, it's the only thing stopping you retrying a dead idea. Step 8. Audit your assumptions. List every belief this situation depends on, especially the ones that feel insulting to check. The request is arriving. This function is being called. The file I'm editing is the file being executed. My build actually rebuilt. I'm on the right database. Now verify each one with an observation, not by thinking about it, by looking. The bug is almost always inside the assumption you are most confident about. Confidence is what stopped you checking it. The engineering time lost to editing one file while a stale build of another runs could power a small country. Now, the ones that break the procedure. A Heisenberg disappears when you look at it. You add a print statement and it stops failing. That's not the universe mocking you. Your instrumentation changed the timing, which is itself a finding. If observing changes the outcome, the bug depends on timing, and you've narrowed the search to concurrency. For race conditions, stop reproducing by luck. Run the case in a loop thousands of times, under load with more threads than cores. Then use a race detector, Thread sanitizers instrument every memory access and report two threads touching one address without synchronization, even on runs that passed. For memory, don't guess at leaks. Snapshot the heap, run the suspect operation, snapshot again, compare what grew and what still holds a reference, and check the boring killers. 0, 1, empty, negative, maximum, 1 past the end. A surprising share of incidents are a comparison that should have been inclusive. Step 9. Close the loop properly. You found it. Before you ship, make sure you can explain the mechanism, not the fix. The mechanism. Then ask why it worked before. If the code was always wrong, something changed to expose it, and that something is often the real bug. If your explanation is, I changed it and now it passes, you didn't fix the bug. You moved it and it returns under load on a Friday. So write the regression test and run it against the old code first to confirm it fails. A regression test that never failed proves nothing. Then the wider question, one bug or one instance of a class of bug. If the same mistake is possible in 9 other places, the real fix is a type, a lint rule, or an interface that makes it unrepresentable. The best fix isn't the one that repairs this failure, it's the one that makes this category of failure impossible. Finally, 2 moves for when the procedure stalls. Explain it out loud. To a colleague, a duck, or a message you never send. Thought is compressed and skips steps. Speech is linear and cannot. You will hear yourself assert something. Stop mid-sentence and go check it. Forcing serialization exposes a step your brain kept silently skipping, and walk away. After hours on one problem, attention settles into a groove and keeps rerunning a path it already ruled out. Standing up breaks the groove. 20 minutes away regularly beats 3 more hours of grinding, and every engineer has a 6 in the morning story. So, make it deterministic, shrink it, read the evidence, instrument before theorizing, learn the debugger, bisect code, history, environment, and data, form falsifiable hypotheses, audit your assumptions, close the loop with a failing test. Underneath all 9 is one skill, reducing uncertainty per unit of time. That is the entire job. That's the real gap between a junior and a senior engineer. Not memorized syntax, how much the search space shrinks with everything they try. Every bug you fix is a correction to your model of the system. That's not lost time. It's how anyone learns what their system actually does. Now go break something.